Hello students, in this video we're going to discuss about Kirchhoff's law. Kirchhoff's law, right, and Wheatstone bridge principle. Okay, Kirchhoff's law and Wheatstone bridge principle. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. And if you want to follow me, then this is my Insta ID OJHA LAKHYAJIT123. And if you need the PDF of the notes of this chapter, then send a message to this ID. So I will provide you the notes. Okay, because in this video I'm going to explain only. This is not for the notes. Okay, so let's start. So first, let us discuss about Kirchhoff's first law. Kirchhoff's first law. Kirchhoff's first law. Sorry. This first law is also known as junction rule or junction law, right? So according to this, in a circuit, so at the junction total current is zero. That means suppose, so I current is coming here, I1, here I2, and suppose I3 current is going out, then I4 current is going out, then current in, that is I1 plus I2, and current going out I3 plus I4, that's equal. So that's why their sum, that is I1 plus I2, and those current going out will be taken as negative. This total current is equal to 0, right, at the junction. So hope you have understood this. And according to the second rule, so Kirchhoff's second law, what happens here? Kirchhoff's second law, or this is also known as loop law or voltage rule. So it states that the algebraic sum of all the voltages and potential differences, voltages means here potential differences across all the elements and EMF of all the sources in any closed electrical circuit is 0. Suppose we have a circuit here. So here we have a cell and we have a resistor. This is also there are two elements, suppose. Then so there must be a potential difference between these two ends of these elements. If I current flows through it, then potential difference across this must be equal to IR, right? So potential difference across this will be IR, right? So according to this rule, this EMF plus IR, this total voltage will be equal to 0, right? Sum of all the voltages and the EMF of all the sources enclosed in this connected in this closed circuit will be equal to 0. Okay, so here we need to learn sign convention to apply this rule. What is the sign convention? So let me show you. Suppose we have a resistor here R, current is in this direction, this is the direction of current I, suppose, then potential difference across this resistance is, suppose, then it will be IR according to Ohm's law, right? IR, but it will be positive or negative. So when we're gonna apply this rule in a closed circuit, when we're gonna apply this rule in a closed circuit, we have to choose a path, either clockwise or anti-clockwise. So it's your choice, whatever you want to choose, clockwise or anti-clockwise. Suppose if we choose the direction in this way, suppose in this way, then this will be the direction, right? So this is the path of direction of the path that we have taken. So this is the path. Suppose if the path and the direction of the current is same, then we're gonna take this as negative, right? And suppose this is the direction of current, this is resistance R, then voltage is IR. If the path is opposite to the current, then we're gonna take this as positive, right? Okay, before that let me tell you one more thing. Now suppose we have a cell, how to deal with this? Its EMF is suppose E, and so the path is suppose from the positive terminal to negative terminal. In that case, the EMF should be taken as negative, positive to negative. It is higher to lower potential, so potential drop. Okay, and if the path is from negative to positive terminal, if the path is negative to positive terminal, then we're gonna take this EMF is positive, so it's potential gain. We're gonna choose that in that way, right? Hope you have understood this. Okay, right, now you see, let me tell you one more thing. So you can take the convention in reverse way also. You can take this positive. If you take this positive, then this should be negative, and that in that case here also sign convention will be reversed. If you consider this positive, then it must be negative, right? Hope you have understood this. Now you see, let me tell you, if you consider if you take that path and the current direction is direction of path and current, when it is same, if you take this IR as negative, right? So then you see, then the direction of current, if this is the direction of current, then here you see, we know that current flows from positive to negative direction. That's why in case of cell also, if the path is from positive to negative, that means it is in the direction of current. You can consider that way. And if you consider this positive, then this must be also positive. In that case, this will be negative and this one will be negative, right? Hope you have understood this. So don't be confused. Take only one convention. Let me take this one only. Okay. So now let's discuss about Wheatstone bridge principle. Now you see, in Wheatstone bridge principle, what happens? In Wheatstone bridge, what is Wheatstone bridge? Here you see, it consists 4 resistors. Okay, it consists 4 resistors connected this way, suppose with EMF E. Okay, so now you see there is one more branch. This is galvanometer G. Okay, let me take that way. This is suppose P, this is Q, this is suppose R, this is suppose S, right? So now you see, current flow is suppose I2 and current flow is suppose I1, right? This is suppose I1, and current flow the galvanometer is suppose Ig. In that case, current flow this branch must be I2 minus Ig, because I2 current is coming. Then from here this is split into 2 parts, right? So similarly to this branch Ig and I1, so Ig plus I1. Okay, so hope you have understood this. So total current is suppose I, right? Okay, now you see, in this case, using this Wheatstone bridge, what we can do, if suppose P, Q and R, these are known resistor. Okay, these are known, suppose, and this S is suppose unknown. We can determine this unknown resistor, but here one more thing. So any one of these 3 known resistors must be variable resistors, so that we can arrange this, or we can adjust this resistance of this resistor such that current through the galvanometer becomes 0, Ig becomes 0. Because when Ig becomes 0, then ratio of P to R and Q to S becomes equal. This is called balance condition of the Wheatstone bridge. This is called balance condition. Balance condition. Okay, using this relation, if any three resistors are known, then unknown can be determined, right? Hope you have understood this. Okay, so now let us obtain this condition using Kirchhoff's law, or you can write this relation this way also, P by Q then R by S, right? So let us obtain this relation using Kirchhoff's law. So now let me take a new slide. Now let me draw the Wheatstone bridge again. This is the Wheatstone bridge. So here is the resistor, here is another resistor, here is another resistor. So this is P, Q and R. Sorry, let me write the R here, and this is the S, suppose. And this is the galvanometer of resistance G. G is the resistance of the galvanometer. Here Ig current flows through is, and here you see this is I2 current, and through this branch suppose I1 current. So that's why through this branch I2 minus Ig, then in this circuit, in this branch, that will be I1 plus Ig, right? So now let us apply the Kirchhoff's law in this loop. This is suppose A, B, C, A, and this is suppose C, and this is suppose D. Now let us take the loop A, B, D, A. Okay, this loop, and let me take the path this way, clockwise direction. So here you see, for this resistor, here you see, so for this resistor P, current is I2 and path is taken this way. That means this path and the current direction is same. So according to our sign convention, so we're going to take this negative. So here you see, so resistance, potential difference across according to Ohm's law, that must be I2 into P. Resistance is P. So when as I have taken the sign convention in which current and path is same, then it should be taken as negative. Similarly, applying the same method, now let us apply the same method here. You see, in the galvanometer, the resistance of the galvanometer is G and current through it is suppose Ig, and path we have taken in this way. So here you see direction of the path and this Ig is same, so again it will be negative Ig into G. So now let us take this case. So here you see direction of the path and the current is opposite, so here we're going to take positive I1 into R, and this voltage across this in this closed loop must be equal to 0. Total voltage is 0. So this is equation number 1. Similarly, we can apply the same loop law in this loop. So in BCDB, in the loop BCD, so again I have taken the same direction, clockwise direction. Again here you see Ig is in this direction, as I have taken the clockwise direction, so it is opposite to this path. So again we're going to take this positive Ig into Z. Then here you see clockwise direction, here current and the path is same in the same direction, so negative I2 minus Ig into resistance is Q. And here you see in this case S resistor, here path and the current is opposite, as I have taken clockwise direction. So that's why positive I1 plus Ig into S is equal to 0. Now here you see for balance condition, this is equation number 2. Now let me clean this diagram. Okay, now you see in balance condition Ig is equal to 0 for balance condition. In that case this term will be 0, so this Ig will be equal to 0, this will be equal to 0. So this equation gives you minus 2p plus I1R is equal to 0, which implies that I1R is equal to I2P, and I1 by I2, that's going to be equal to P by R. Similarly, this equation number 2 implies that this G term will become 0. Okay, minus I2G plus I1S is equal to 0. If that is the case, then here we're going to get I1S is equal to I2Q, which implies that I1 by I2 will be equal to Q by S. And comparing these two equations, comparing these two equations, what we're gonna get, that Q by S is equal to P by R. Then if you simplify this, then you're gonna get P by Q, then R by S, right? R by S. So this is the balance condition that we have discussed about here. This is the balance condition of Wheatstone bridge. So hope you have understood this. So thank you for watching. See you in the next video. Bye bye.